Alrighty, and welcome to the first tutorial on hyperbolas. Our first objective we're going to explore here is to graph a hyperbola from standard form. But before we do that, let's get out our sheet of all of our conic sections one last time. We've filled in the top 3 rows, and now we're going to fill in our final row. The way to get a hyperbola is we're going to take our cone. Now, technically, a cone continues on, and it's actually called a double cone. But if we continue this cone on like this, and make another little circular base. When we take our plane this time we're going to make our plane perpendicular to the base, and we're going to slice off. It's actually going to be 2 pieces of our cone, and those are the 2 pieces of our hyperbola. So it's really slicing off the 2 sides of a double cone to get to a hyperbola. Hyperbola, that's an E. We have 2 different hyperbolas. We have vertical ones and we have horizontal ones. I'll do the sketch for the horizontal one first. So we've got a little piece. It looks like a parabola on one side and another piece over here that's exactly symmetric. The whole shape right here is your hyperbola. This is a horizontal hyperbola because it's, going left to right with the x direction, and the standard form for that is x minus h quantity squared divided by a squared minus y minus k quantity squared divided by b squared, all equal to 1. We have vertical hyperbolas as well. So let me draw one of these guys, and again, it's both pieces together that makes the hyperbola shape. This one's vertical because it's opening upward and downward, and that is going with the y-axis. So y minus k quantity squared divided by a squared minus x minus h quantity squared divided by b squared is equal to 1. So we're going to explore these 2 standard forms a little bit more in detail in this tutorial. So applications for hyperbolas, satellites. I can try and draw a picture of this maybe on the next slide. Satellites come towards an object, and then they have to use the gravity of that object to go around, and that's a hyperbolic motion. Sonar, which I believe represents something about sound and navigation and range. Sonar is what mainly ships use to figure out depths of certain things in the ocean. LORAN is another application that ships use. I believe this is long-range navigation. This is so that a ship can determine from a radio beacon its speed and possibly its location in the ocean, and so on and so forth. So we've got some applications of hyperbolas. Okay, let's look at the definition of the hyperbola, 9.4a. The hyperbola is a set of all points in a plane such that the difference of the distances from 2 fixed points called the foci is constant. So this definition is almost identical to the ellipse definition, except that we're talking about the difference of the distances, and that's why the main part of the standard form that we're going to see is a subtraction sign as opposed to the ellipse, which had a sum. Okay, so here's a basic picture of an ellipse. Let's talk about all the different of a hyperbola. Let's talk about all the different pieces. First, one of the most important pieces, of course, is going to be the center, and that's sitting right there, right in the center of our graph. Okay, from the center, we're going to be counting out to the 2 vertices. So we'll count in that direction and we'll count in this direction. These are the 2 vertices. So I'll call this a vertex, and I'll call this a vertex. Okay. There are 2 focal points, or foci. Each one is a focus, and we'll count out past the vertex to a certain point. Let's just put it right there. That's a focus right there. And we'll count the same distance but in the opposite direction. We'll just call it right there. That's also a focus. together makes up two foci. Okay, and the last part, the last two things that we're going to be finding are the asymptotes of our hyperbola. And the asymptotes will make, we're going to dot them in, will make a nice crisscross X. It should be straight lines. I'm doing the best that I can. Right through the center. Let's try this here. And that's not too bad. That will help us to place our curves of our hyperbola exactly where they're supposed to be, because the curve is going to get infinitesimally closer to this asymptote, but it's not actually going to touch it, okay, on both sides of that and on both sides of this. So these are the asymptotes. Yep, there's a P in that word, asymptotes, right there. Okay, so we're going to be looking for the center, we're going to be looking for the two vertices, we're going to be looking for the two foci, and we're going to be plotting the two asymptotes before we graph our hyperbolas. So let's first explore the horizontal hyperbola. The big idea here that this is a hyperbola is that there's a subtraction. There's a difference between our two quadratic terms. How we know that this is a horizontal hyperbola is that the x term is first. It's all about the x term, or which term comes first for the hyperbola. If you remember, for the ellipse, it depended on which denominator was bigger. But this time, since subtraction, the order matters, the first term makes us either have a horizontal hyperbola or a vertical. Since the x term comes first and the x is going horizontally, like the x-axis, then we have a horizontal hyperbola. So the first point that we might go and find is the center. That's what I would always go and find first. Let's not abbreviate this first time. The center. And the center, like all the other conic sections, is going to be the h and the k. H coming from the x quantity and k coming from the y quantity. So there we go. So we've got our hk right there. I'll go ahead and put that right. Oops, excuse me. That's a k. H and then k. Okay, so that's good. We're looking for our vertices next, most likely. And the relationship we need to remember of our vertices, first of all, they are ordered pairs, so I'll go ahead and do that. Is that ordered pair and another ordered pair. The vertices are right here and here, and that distance is exactly a units. So that's very helpful, since that's exactly what it would be for an ellipse. We counted a units away from our center in each side, and we have our vertices. Okay, so that's how we find the vertices of the hyperbola. When we're looking for the foci, again, it's going to be two ordered pairs, so we'll find those two ordered pairs. This time, we're counting c units out to the focal point. So this distance is exactly c units. And in the opposite direction, let's say it's about right there, the opposite direction, that's exactly c units as well. So again, incredibly helpful, because that's the same exact thing for an ellipse. We counted c units to get to the focal points. So that's c. Now you might say, well, wait a minute, I don't know, see where c is. A is clearly right here, and well, the square root of a squared would be a, and the square root of b squared would be b. C has that relationship, but for a hyperbola this time, it's the square root of a squared plus b squared. So we need to make sure we remember that. And it's going to be pretty obvious. I know some people might confuse this relationship with C with the one with the ellipse, but it has to make sense, because for a hyperbola, C has to be a longer distance than the value of A. It has to be a longer distance, because if you want to think of this as a little Pac-Man guy, he's got to still be eating the focal point. Okay, so since C has to be bigger than A, we must be adding something to the value of A squared. So that's how I remember that. Okay, in an ellipse, that would be inside. C is something that's less than the value of A, so that's why we're subtracting. Okay, in a hyperbola, a squared plus b squared, the square root of that. Okay, we do have our two asymptotes. And the equations for the asymptotes for a horizontal hyperbola, y minus k equals plus or minus b divided by a times x minus h. I like to represent my asymptotes in point slope form, because if I use point slope form, I can easily just start with the center point and then use my slope. Now, how do I get my slope? Well, the value of b, which is underneath the y term, divided by the value of a, which is underneath the x term. Of course, the square roots of each of these. How I remember that is slope is always the rise divided by the run, which is always the y's divided by the x's. So if I remember this, whatever letter attaches to the y will be in the numerator. And since that's the value of b, then I know my slope is going to be b divided by a. So we'll talk about that when we graph one. I'm not going to dot them in here because this is already a pretty picture. Okay, let's graph our first horizontal hyperbola. First of all, now that we've seen all four conic sections, we need to know why this is a hyperbola. I see that we have two quadratic quantities. Since there are two of them, it cannot be a parabola. Since they have different denominators, it cannot be a circle. And since it's a minus sign here, this must be a hyperbola. Since the x term is first, this is a horizontal hyperbola. Horizontal. Okay, so let's find our center first. Our center comes from HK, so this is positive 4 and that's negative 3. Let's plot that as we go. 1, 2, 3, 4. Negative 3 would be right there. Again, I know that this is horizontal, so I'm going to be taking the value of A, which the value of A is 4, square root of 16, and I'm going to be counting 4 units horizontally from my center. 1, 2, 3, 4, and 1, 2, 3, 4. These are the vertices of my hyperbola, and now let's name them. That's 1, 2, 3, 4, 5, 6, 7, 8, negative 3, and 0, negative 3. I'll label that with a V. 8, negative 3, and 0, negative 3. Okay. The focal points come from the value of c. So let's see what that is. Square root of a squared plus b squared. So c is going to be the square root of a squared and b squared are 16 and 9. So I'll add those up and get 25. The square root of 25 is 5. So that's kind of nice. C is not always a nice number, but in this case, it is. So let's count out 5 units, which will be right here. 5 units here. So this is 9, negative 3, negative 1, negative 3. Alrighty. We're flying through this now. Negative 1, negative 3. Okay, there's my focal points. The last thing I need are my two asymptotes. The equations of my asymptotes will be y, I just take this quantity basically, y plus 3, equals plus or minus the value of b, which is 3, divided by the value of a, which is 4, times, and I just steal this quantity, the x minus 4, and there we go. These are two different equations. One has the positive 3/4 slope, and the other one has the negative 3/4 slope. Let's plot these. Since it's point slope form, I know one point that's on this line is at 4, negative 3, which, lo and behold, happens to be my center. And then from my center, I'm going to be doing each of these slopes. Let's do the positive slope first. Positive 3/4 from my center would be going up 1, 2, 3, and then over 1, 2, 3, 4. It doesn't look like I can do another one, 1, 2, 3, and over 4, so I won't. But I can go down 3 and to the left 4. Down 3 and to the left 1, 2, 3, 4. I want to get as many points as I can, because the more points I can get, the easier I can make my line nice and straight for my asymptote. Okay, and then the same point on the other line, but this time with a negative slope. So I'm going to start right here at my center and then go down 1, 2, 3, and over 1, 2, 3, 4. Since I'm finished over here, I'm going to try and get some points over here, which is up 3 and right 4, up 3 and right 4, up 3 and right 4. I'm going to get as many points as I can, maybe even get out a ruler so that I can make it a nice straight. Please dot them in. This is not part of your hyperbola, it's just a method of making your hyperbola fit nicely. And now that I've got everything, remember where the vertex is. He's going to be eating the focal point. So I'm going to draw in my hyperbola, getting closer and closer and closer to the asymptote, but please do not touch the asymptote. I'm okay with the little arrowhead touching the asymptote. I'm just not okay with the curve itself touching the asymptote. So we'll go like that. And please do not curve away from the asymptote either. That's sloppy. You're getting closer and closer and closer, and there is a weird looking graph, and the black curves are the hyperbola. There we go. That's our horizontal hyperbola. Okay, now let's look at what a vertical hyperbola will do. So we've got a vertical one, and it's going up and down in the y direction, which is the big reason why this is vertical. The y term comes first. So that's my big thing that I'm noting right now. I know that it's a hyperbola because of the minus sign, but now I need to know what type. The y term is first. So since the y term is first, this is a vertical hyperbola. And watch out because things are a little bit backwards. When I'm looking for my center this time, I know that it's still hk, but look at where h is. H is always with the x quantity, and k is always with the y quantity. So please don't mix that up. Okay, so there's my hk, and I'll go ahead and put that in here. Here's hk. Everything else is identical, it's just that we're going vertically. So when I'm looking for my vertices, I'm still going to be counting A units from my center, this time up and down, to get to my two vertices. And it's still going to be two ordered pairs, so I'll go ahead and put two little ordered pair shells there. I've also got my two focal points, which again is still going to be C units away from the center. I'll put it about right there. C units away from the center is still the focal points, or the foci. And my asymptotes, I'll just label that with a big A, it's still y minus k. It's not quantity squared, of course, we're talking about a linear. Plus or minus, this time, the slope is A divided by B. Now you might say, well, wait a minute, how am I supposed to remember that? Well, again, since slope is y's over x's, think about which number associates with the y. This time, since the y term is first, A is associating with the y. And since the y's divided by the x's will be the slope, A divided by B will be the slope. Again, we're taking the square root of everything from our, everything squared here, but in our linear equation, nothing is squared. Okay, and those are our asymptotes. And I'm not going to put them in here again because we got a nice pretty picture. Let's graph one vertical hyperbola, and that should be enough, one horizontal and one vertical for you to see. Okay, again, I know that this is a hyperbola firstly because there's a subtraction in between my two quadratic terms. I know that this is vertical this time because the term that comes first is the y term, and the y-axis goes up and down vertically. Okay, so I'm looking for my center. My center comes from h, which is 2, and k, which is -1. So let's plot that out. 2, -1. There's my center. We're in the fourth quadrant again. Okay, that's fine. Vertices, I'm still figuring out what the value of A is. A is always from that first term. In this case, it is 5. Okay, and since A is with the y, makes it vertical. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So those are my two vertices. Let's go ahead and count those out. That's 2, of course, and then 1, 2, 3, 4, and 2, 1, 2, 3, 4, 5, -6. So 2, 4, and 2, -6. My focal points, well, now I need to figure out what the value of C is. So I'll come over here and use this little algorithm. C is the square root of a squared plus b squared. So C is the square root of, I'm going to take these two denominators and add them up. In this case, it's 25 plus 16. So C is the square root of 41. So that means then I'll be using my calculator and approximating, since that's not a perfect square, and from the calculator I'm just approximating to the tenths this time, since I'm graphing it, approximately 6.4. So I'm going to be counting up and down 6.4 from my center. 1, 2, 3, 4, 5, 6.4-ish is right there, and then down from my center, excuse me, 1, 2, 3, 4, 5, 6.4 this way. So it's approximately right there. Let's actually see what those 2 points are. 2, of course, 1, 2, 3, 4, 5.4. So 2, 5.4. And the other one is 2 and then negative 1, 2, 3, 4, 5, 6, 7.4. So 2 and then negative 7.4. I know some people had some questions in our last practice with the ellipses. Do you want us to use the actual radical or do you want us to use an approximation? I'm fine with either. If you want to answer your 2 focal points saying that it's 2, let me do it right here. 2, of course, and then the center, which is negative 1, plus or minus the square root of 41. If you really want to do it like that, that's absolutely fine. Understand that, of course, the x-coordinate of the 2 focal points is 2, and then the y-coordinate is going to start with the negative 1, since that's what the center started with, and then we're adding or subtracting the exact value of c. So that's fine with me, either one, if you want to just count it out by approximation or if you want to use the exact value. As long as it's correct, that's fine with me. Okay, so let's talk about our asymptotes. Our asymptotes are going to be y. Let me just steal this quantity right here, y plus 1 is equal to plus or minus, let me get my letters correct, since the y's over the x's would be the square root of this is 5, the square root of this is 4, I'm talking about 5/4 for my slope. And then let me just steal the x quantity, x minus 2. Those are my asymptotes. Let's plot those in. I know the point is 2, negative 1, which again is our center. That's the whole point of using point slope form. And then the slopes are 5/4 and then negative 5/4. Let's do positive 5/4 first. We're counting up 5 and then over 1, 2, 3, 4 to the right. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, I can do a little bit more down this way. Down 5, but left 1, 2, 3, 4. I think that's about it. So I'm plotting that. Again, a nice ruler would be helpful, unless you have a nice steady hand. Okay, and then negative 5/4, which means I go down 5, but this time to the right 4. 1, 2, 3, 4. I'm not going to do any more over there, so I'll go up up 5, and then left 1, 2, 3, 4. Up 5, and then left 1, 2, 3, 4. I believe that's right. 1, 2, 3, 4, 5. There we go. And sound effects are optional, of course. And there we go. Remember that the focal points are going to be eaten by the actual curve of the hyperbola. So this is our vertex, because you've got 2 dots here. You don't want to mess it up at this point. You've done so much. This is our vertex. So this is where our curve starts, and it starts curving closer and closer and closer to that asymptote without touching. And then same thing symmetrically on this side. And then down here, it's curving this way and then this way. Alrighty. And that is the graph of a vertical one. Thank you very much for watching this tutorial on the graphing of hyperbolas, and we'll see you next class to practice this some more.